An elevator into space. Sound crazy? A far-fetched idea? Impossible? Not so fast. In the late 1800s, a Russian looked at the Eiffel Tower and said, why not? If we can go that far, why couldn't we have something go into space? And in the 1960s, another Russian scientist actually proposed an engineering design to build an elevator into space. Hi, I'm Dave Cederberg, Outreach Coordinator for the Department of Physics and Astronomy at Purdue. And we're going to talk about building a space elevator. Consider, if you would, the Earth, a satellite in geosynchronous orbit. And as the Earth rotates, the satellite maintains a constant position relative to the surface of the Earth. Let's say from the satellite, we fabricate a cable beginning at the satellite and extend it down to the surface of the Earth. Beyond the satellite is a secondary cable that goes to a counterweight. The counterweight, also in geosynchronous orbit, exerts a tension on the cable, keeping it taut, providing a means of a vehicle getting from the Earth up to the space station. This would provide a more economical means of getting people and cargo into space and then easily beyond. It's much easier to launch another vehicle or to launch a vehicle from the satellite than it is from the Earth. It takes a lot less energy. Well, NASA scientists and American engineers took the idea seriously and in the 1960s began to draw designs and make plans to build an elevator into space. However, the one constraint that the design relied on was finding a material strong enough to build the cable. We could build a satellite, we could build a counterweight, we could build a transport vehicle, the carrier, but we didn't have a material strong enough for the cable. And so the design plans kind of came to a halt until the early 1990s when the carbon nanotube was discovered. Carbon nanotubes are a particular form of carbon, a tube-shaped molecule composed entirely of carbon atoms with superior strength and very light weight. With 200 times the strength of steel, scientists began to think this might be the magic material. It might be a component that could be part of the ribbon material to actually make the space elevator work. So in our experiment, students will take a piece of polyethylene plastic, simple painter's drop cloth. They will put it in an apparatus and stretch it to see how much it stretches relative to its original length. Then they'll take the same material and create a composite. For example, here we've sandwiched together two plastic sheets, and in the middle are fibers that would maybe resemble carbon nanotubes. Students will take this piece, cut it to the same dimension, and again, test its tensile strength. So the materials we're providing, if we're providing materials for you, here's what you will get. We will provide you with several examples or several samples. We will provide you with several samples of different kinds of polyethylene material. We've labeled them with the thickness, 1 mil, and the brand. We tell you the brand so that you can replicate your experiment if you want to go out and buy the material. We're going to provide you with an adhesive, in this case some Elmer's rubber cement. We have a spring scale, which we'll use to apply a force. We have some wooden blocks, and to the wooden blocks we've attached a gasket material so that when you sandwich the plastic between to be able to hold it securely, it grips a little better with the gasket material. We will give you a device we'll just say this is a spring support. The spring will actually, this will get clamped to a table. The spring hooks over the hook or over the bolt, and this end will attach to the material you are testing, and you have a means of holding this securely. We will also provide you with a quick grip clamp to be able to attach the board to a table. We'll give you a couple of C-clamps which will be used to clamp the material in place between the wooden blocks. And we will provide you various materials with which you can make the composite material, things that you can sandwich between the plastic. So we have some mesh fabric, we've got some string, and we have paintbrush. And the paintbrush bristles can be cut off and used between the plastic to actually model what maybe a carbon nanotube might be like in this kind of application. Things that you will also need, which we will not provide, you'll have to provide these yourself, would be some painter's tape, some regular 8.5 by 11 printing paper. We've cut it to 8.5 by 6. You'll need some wax paper, you'll need a ruler, and if you want to try something in addition to the Elmer's rubber cement, you might try a spray adhesive. However, I would warn you that this requires more ventilation and may be a little messier. And finally, if you plan to do this with your students, you may be cutting a lot of plastic. Yes, you can do that with scissors, and yes, your students could do that themselves. However, scissors don't cut this really well. It's a thin material, and your scissors have to be really sharp, and it may not be practical for students to do that. Personally, I would cut the material to a pre-cut size, ready to give to my students. And to do that, a rotary fabric cutting tool is very handy. So this tool will very easily cut plastic very quickly, as well as other materials. Now, it's very sharp, so you want to be careful, but it really saves a lot of time. And the rotary cutting wheel is also very handy when you want to trim the fabricated ribbon to the exact length to be tested. We're going to want it 4 centimeters, so I'm going to kind of just eyeball that and go ahead and cut this to 4 centimeters. And see how quick and clean that is? Your students could use this also. However, this is very sharp. When not in use, make sure you always retract the safety guard. In addition to providing your students the opportunity to do an experiment related to real-world applications and research, it also gives them the opportunity to talk about things related to such a grand project such as the space elevator. So for example, political applications, political consequences. Who will build it? Who will maintain it? Who will take control of it? Who might overtake control of it? How might it be affected by weather, by unexpected consequences? Just because we can do it, does it mean we should do it? And what about the meld between technology and engineering, and do we have the materials? These are interesting questions to debate and provide your students an opportunity to extend their learning beyond the classroom to talk about real-world consequences and real-world applications. So, let's get started and do the experiment. Your students will make and test 2 different materials. The first one will just be a sandwich of the polyethylene ribbon. The second one will be polyethylene with another material in between, a fiber of some kind, to make a sandwich so that the only difference between the two will be the composite additive between the two on the composite material. So to do this, I'm going to put down a piece of wax paper, as you see, and tape the first ribbon in place. It helps to have the tape already handy and cut. These are about 2 inches by 8 inches. You could give your students 2 inches by 16. They could cut it in half, or you could provide the right size for them. The second one, it's going to be difficult to handle this with glue on it. So I'm going to take just a piece of paper, just printer paper, 8.5 by 11. Well, it's an 8.5 by 11 piece, cut down 8.5 by 6. And I'm going to mark off. I want to make a frame, basically. And now I have a frame that I can attach the second ribbon. And I can easily handle that then with glue on it. So let's go ahead and glue the first one together. These will be trimmed to an exact dimension of about 4 centimeters by 15 centimeters to do the test. Okay, so that's in place. I'm going to cover that with a second piece of wax paper just to help maybe push it down and flatten it out. Now you could also put a weight on this and cover it for a little bit, like with a book. However, within a few hours, the solvent from the rubber cement will leach through the wax paper and it will damage your book. So don't leave something on there a long time. Okay, now we will do the same thing and create our composite. For my composite this time, I'm going to use string. What I'm going to do is take my 5 or 6 feet of string and cut it into pieces. And think about the design that how I might like to arrange these pieces in order to have the maximum strength. Okay, I've gone ahead and cut the string into pieces. These could actually model the carbon nanotube fibers that might be added to make a composite material. When we started doing this originally, we gave all students the same material, and that was string. And we had the students create a design where they would draw out on paper how they would arrange the string pieces in their composite. So do they want to go in cross patterns? Do they want to go parallel? Do they want longer pieces, shorter pieces? And that could be part of the design process. So the working time on the rubber cement is not long, so we don't have a ton of time. Okay, so I'm going to label what these are. I used 1 mil film guard in this experiment. There are plenty of brands of plastic out there. I've always been kind of fond of film guard. However, I think the only place I can find it now is on Amazon. But you can try other brands too. If you want to try 1 mil Husky, that's fine as well. You see the appearance is a little different though. So they have potentially different properties. So I'm going to write here 1 mil, film guard, no composite. And this one, 1 mil film guard, string composite, okay, we'll press those down and then maybe give them a little weight for, half an hour. And that's not totally necessary. If you just press it down and cover it with wax paper, you should be fine. The final size of the ribbon for testing, we want to be 4 centimeters by 15 centimeters, and then we'll clamp that into place. This composite is actually with paintbrush bristles. Now I could cut this with scissors, or I could cut it with the Rotary fabric wheel. Let's just go ahead and do this one with scissors. Okay, so to do my tensile test then, we will clamp this in place between the 2 wooden blocks. This works best with about 3 students. 2 students can do this better than 1, and a 3rd student during the tensile test, 1 student can apply the force, 1 student can record data, and 1 student can read the Newton scale. Now I would like a finished test strip of somewhere around 10 centimeters. It's not critical. What's critical is you kind of need to be squarely in the squarely clamped between the wooden pieces. Okay, so we're ready to put that into position and do our tensile test. When you're ready for your tensile test, attach the support board to a table with the clamp. If you're doing this with your students, don't let them put the clamp up this way. Put it down that way. It'll be less dangerous. The spring scale goes over the bolt, so you can read the numbers at the top. And the C-clamp fits onto the hook. So with everything in place, we can read the Newton scale, we can apply a force, but we need a means to measure the length of the ribbon in between. We want to know its original length and how much it stretches. So in order to do that, we will just tape a little ribbon, ruler ribbon, in place with a 0 at the first block. And then as we stretch, we can measure the length of the ribbon as it stretches. So I will make a note of my original length, which is with 0 force about 9.9 centimeters. Okay, and I think we're ready to start. Okay, this is the film guard ribbon. No composite, just the ribbon. Our initial length is 8.7, and we're ready to go. 2 newtons, 8.7. 4 newtons, 8.7. 6 newtons, 8.7. 8 newtons, 8.8. 10 newtons, 9.